Okay, let's go ahead and get started today. I debated as to whether or not to spend one of our classes talking about quadratics, but I decided that there are just too many important topics, and quadratics is one of those topics where things can get more and more challenging, and it's good to have a very wide set of experiences with quadratics, and we're going to definitely discuss some harder problems that involve quadratics, but we are going to start from the very simple and make sure that we all have a very common understanding of what to do with quadratics. So let's go ahead and take a look at problem number 1 here. And let's talk about some solutions. What if you have an equation x squared equals something? What about x squared equals 0?
X is 0.
X is 0. That's the only possible solution. How do you know?
Because 0 squared is 0 and root 0 is 0.
And a positive squared, a positive times a positive is a positive. A negative times a negative is a positive. So 0 is the only possible number we could put in there. Okay, what about x squared equals 1?
1 and minus 1.
1 and minus 1. Okay, good.
Minus 1.
So we're taking the square root, but you all seem to know already that if we multiply that same negative times a negative, we end up with a positive. And we might even say, hey, negative a squared equals negative 1 squared times a squared, which is 1 times a squared, which is a squared. So after a, we're going to get 2 solutions for each of these. What are the solutions for part C?
3 and minus 3.
Or there's a specific symbol. Yeah, that's the.
What about D? X squared equals 12.
Plus or minus 2 root 3.
I'm going to say x equals plus or minus the square root of 12. We're undoing the square process. And this is important. I just said undoing the square process. We're going to see much harder quadratics than this. And what we need to do is go from something that is quadratic to something that is linear, something where the variable is just raised to the first power. And in order to do that, we take the square root when we can. How about x squared equals 225?
X is plus or minus 15.
Plus or minus 15.
Okay, so most important thing, we take a square root. Okay, let's take a look at some more. What do we do with part A?
We can start.
We don't need to expand, so first we could find the square root.
Okay, take the square root. Seems reasonable.
So then x is equal to
10. X is plus or minus 2.
Not plus or minus.
It's just 2.
My bad, sorry.
Yeah, we just add 2 to both sides and we get our one and only solution. How about part B?
Minus 2.
Yeah. No, not yeah, minus 2.
There are going to be 2 solutions to this one.
So it'll be x plus 3 equals to plus or minus 1.
Good. We start by taking the square root. X plus 3 equals plus or minus 1.
So x equals to 1 minus 3 and minus 1 minus 3.
Good.
Which is
minus 2 and 4.
Be careful the way you say it.
Minus 2 and minus 4.
Good.
Oh, sorry, my bad.
And if we wanted, we could write, well, if we wanted, we could write x equals minus 4 and minus 2 that way, or we could say x is an element of the set that contains only minus 4 and minus 2. And you might even see set building notation, x, such that x equals minus 4 or minus 2. You'll see more and more types of set notation as you go. Just begin to absorb them. It's just the way people communicate. Part C.
X plus 19 equals to plus or minus 3. X equals minus 19.
Okay, part D.
X minus 1 is equal to plus or minus root 13. And there's no way we can simplify root 13, so it's just x equals plus or minus root 13 minus 1.
Close.
Oh, plus 1, my bad.
We add 1 to both sides. And we get 1 plus or minus root 13. Okay. And now part E.
X minus 15
X minus
equals
15
to
is equal
plus
to
or minus
12.
12.
So plus or minus 12. So x is equal to 15 plus or minus 12, which is then x is equal to
27 or 3.
yes.
Okay. So even when it's not just x squared on one side, if we can take the square root, we win, right? So take the square root. That's our goal. Okay. Can we take the square root with these?
We'd have to factorize first.
How do we rewrite part A?
We
X plus 1 squared.
X minus 1 squared.
Now we can take the square root. And we get our one solution. Okay. Part B. How can we rewrite part B?
x minus 1 squared.
Now we can take the square root. And what are our solutions?
2, negative 2. What am I saying? 0 and negative 2.
0 and 2.
Wait, excuse me, could you please go over the factorization? I'm not so familiar with factorization.
Okay. So here's what's going on. Let's talk about squaring binomials. And this is good. This is exactly why I wanted to go over this and find which pieces somebody here might not be familiar with, because you're going to use quadratics a ton. They are everywhere. If you're walking along the road and you look under the bottom of your shoe, there's probably a quadratic under there. So squaring binomials. for the moment, we're going to stick with simple ones. If we were to square x plus 1, well, that's x plus 1 times x plus 1. And we can break either of these apart. What are we doing here?
We're expanding the brackets.
What property are we using?
Expansion.
The FOIL method.
The FOIL method is shorthand for the
This is the
distributive property.
Yeah, this is just distributive.
Right. This is the distributive property right here.
But we can also use the formula.
Well, I want us to understand where any formula that we use comes from, or any method that we use comes from, because you can't use something creatively unless you understand where it came from in the first place. And I want all of you to be able to use this creatively. So here we are. We've got these 4 pieces, and now we add them up. And 2 of them are like terms. X and X we can add to get 2x. So now let's talk about this FOIL. Here's what people refer to as FOIL. It stands for first, outer, inner, last. And what that means is we multiply the first term of each binomial, x times x. We wound up with x squared. And then we do the outer terms, x times 1. And we wound up with an x. And then the inner terms, 1 times x, and we wound up with another x. And then finally we did the last terms, 1 times 1, and we wound up with a 1. First, outer, inner, last. Yeah, there are 4 pairs, right? There are 2 terms in the first binomial and 2 terms in the second binomial. And therefore, we should get 2 times 2, 4 terms. 1, 2, 3, 4 terms. If some of them are like terms, and they are here, then we can combine them to produce the middle term. So very often, you know, if we just have like a 1 variable binomial, we wind up with 3 total terms after we combine like terms. The 2 linear terms that have x to the first power usually combine. So let's take a look at a couple of examples, a couple more of what this looks like. X plus 5 squared. And I want somebody who doesn't already have a lot of experience to offer their answer here. Whoever it was who asked about this.
So it would be bracket open, x plus 5 another x plus 5. So then you get x squared plus 5x plus 5x again plus 25.
That's very good, David. And we can combine those 2 5x terms, the like terms, and we get x squared plus 10x plus 25. Okay, how about x minus 7 squared? Manvindra?
Yes, please. Okay, this would be x squared Wait, I'm trying to calculate it using the formula. So x squared minus. Let me. Okay, so that's x squared minus 7x minus 7x minus 49. That's x squared minus 14x minus 49.
You're very close. What's the last? What
Plus
is
49. Plus 49. Sorry.
Okay. Does anybody notice anything interesting about the terms in all these cases?
Yeah.
What do you see?
They're in decreasing powers of x.
That's true. And, you know, we almost always choose to write our polynomials that way just for the sake of organization. We write the biggest power of x on the left, or the biggest power of whatever variable we're working with, and we decrease in terms of powers, and that's just organization. But what about the coefficients?
For example, when we have x
Anahita, you're breaking up on me.
plus 5 squared, the coefficients, yeah, it's a 10. Oh, can you hear me now?
I can hear you now. Thank
Hello?
you. I can hear you.
Just saying that the result we get, the 10 and the 25, they're multiples of 5, just like how for x minus 7 all squared, 14 and
Okay, Anahita is pointing toward a relationship between the coefficients. Somebody else, see if you can put that into words.
May I try?
Sure.
So we have x plus 5 squared. So the last term is 25. Is supposed to be the multiple of the two values. If it's 5 and 5, it should be 5 times 5, and the 10x, the coefficient of x, should be a sum of those two factors.
Okay,
Okay,
and
can
we're
I
just
try?
talking about squares here, so it's even easier.
Can I try?
So I'm going to list just a few examples right here, and somebody tell me what is the easiest pattern that you see, or the easiest relationship.
So you basically square the first one, and then plus for the like something like for the x plus 2 squared. For that one, you just basically square the x plus 2. So you have to times the whole thing by 2. So x times by 2 times by 2. The 2 is already there. It's like a formula. Yes. So you times the 2 by 2 times x. Yes. And then you square the last number. So the formula is x squared plus 2ab plus, a squared plus 2ab plus b squared.
Yeah, we always have x squared. If we were to do this generally and say x plus a squared, we're always going to have x squared, and then whatever that constant term is, a, we're going to have 2 of it multiplied by x, because we're going to have an a times x and an x times a term. And then finally at the end, we're going to have a squared. So this is for squared binomials, but we like squared binomials. We like perfect squares. Why do we like perfect squares?
You can just find the square root and make it linear.
So that we can just take the square root and get a linear equation, or 2 linear equations, I guess we could call it that, since we have a plus and a minus. Okay, great. So we know that our fundamental goal is to take the square root. We know that sometimes the squares are not pre-packaged for us, so we need to be able to recognize them. So we're on our way. So part C. Somebody turn this equation into an easier equation for me.
X plus 2 squared.
Okay, now what?
We find the square root, so it's x plus 2 equals to plus or minus 3.
And now?
We subtract 2, so we have x equals to minus 2 plus or minus 3.
And what are these solutions, Sneh?
Minus 5 and 1.
All right, great. Let's move on to part D.
X minus 3
X
all
minus
squared.
3.
All right, Rishabh, what can we do now?
X minus 3 would be the square root of 18. Plus or minus square root of 18.
Good.
And so then it's 3 plus or minus 18.
Right, 18.
I mean x plus or minus root 18.
Yeah, root 18. We can pull out a root 9.
3
Yeah.
root 2.
Yeah, we get 3 root 2. Any perfect square factor, we can always separate out. So I always separate out the largest square, even if I do it in pieces. And finally, what are the roots?
3 plus or minus 3 root 2.
There we go. And imagine for a moment, could you eyeball this equation and find those roots? Do you look at that equation and go, I bet I can plug in 3 minus 3 square roots of 2 and solve that equation? Unless you have a tremendous amount of experience. You probably don't just look at that and think, I'm just going to eyeball that equation and plug in some values and figure out what they are. Use my number sense. So already we're doing something that would have been very difficult to do otherwise. Let's take a look at E. Somebody prepackaged or repackage that for us.
X plus 6 squared.
Great.
What is the square root of 400?
20.
20.
Now we can take a square root. Okay. Let us continue our journey. Okay. What is different about part A than anything that we've seen so far?
There are no terms without a variable.
That's true.
C is equivalent to
I couldn't understand. Was that Salorm?
Yeah, I was just saying that I think most people call it C. C was equivalent to 0 in the equation.
Yeah, we have no constant term, or 0 as the constant term. So let's just take the square root, right?
No.
No?
No.
Because the square is only on one thing. we'd have
We factorize.
Well, we could try to factor. Okay, this one does happen to factor. So if you can factor, what do we know?
now we know that
X plus 2 is equal to 0, so x will be -2.
Okay, yeah, there's a principle where if the product of two numbers is 0, well, one of them has to be 0, at least one of them. So we know that x equals 0 or x plus 2 equals 0. And this gives us the solutions x equals 0 and -2. Okay? So I'm going to do this in a second way. Up to this point, we've been able to take the square root every single time. Maybe we don't need to. Maybe some of you know how to factor or will learn how to factor well enough to solve a lot of these quadratics. But I would like to know how to take the square root. But if we just take the square root of this one, how does the left-hand side simplify?
I think we could square the equation.
Well, that puts us back where we were with a quadratic. That's the complication. We want to be able to get rid of the second power of x. So here's the thing. This does not have a square root that is a binomial. Not something simple like we were looking at before with all these other examples. Not every trinomial is a perfect square trinomial. X squared minus 16x plus 64 is, but x squared minus 16x plus 65 is not. Well, could we do something to the equation?
Yeah, could I propose a solution?
How do we solve this problem?
Could I solution?
What can we do to change this equation?
Can we divide it by x?
So I'd rather not divide because I'd rather not lose a factor. If anything, I'd prefer to factor than divide.
If the number on the right-hand side was not 0, then you could bring it to the left-hand side and say it's equal to 0, but it's not.
So what I'm going to say is I'm devoted to the idea that I want to be able to take a square root. And here's what I'm going to do. I'm going to add 1 to both sides. Now what?
Now we can factor the x plus 1 squared.
And we get the same solutions we got before. So this that we did right here, this is known as completing the square. And some of you, the older students, you may have seen this before. Are there a few of you who've seen this?
Yeah.
Yeah.
Yes.
Yeah.
Okay, so at least a few of you have seen this before. So here's one thing I'm going to go ahead and tell you. Later on today, we are going to derive the quadratic formula. We're going to discover it ourselves. But what I thought was true when I first learned this level of algebra, I thought the quadratic formula was the most important thing. But as I got older, I realized that completing the square solves a million problems. I mean, it's everywhere. There is a good need to turn quadratics into a squared form, whereas the quadratic formula solves one type of problem. It just gives us the roots of a quadratic, or the solutions to the quadratic equation. By the way, does everybody know the difference between those words, root and solution?
Yeah.
Yeah.
What's the difference?
The root would be the roots of x. Wait, no. I learned this a while ago. Someone else can go.
I'm not sure how to put it, but the root of the equation, like for the quadratic, would be the b squared minus 4ac. And the solution is the actual value you get after you solve.
So b squared minus 4ac is the discriminant, and we'll talk about that later. But here's the thing. If I ask for a root is something that turns an expression into 0. So we say that x squared plus 2x has roots, 0, and -2. A solution is a value that satisfies an equation. So the solutions to the equation are 0 and -2. So that's the difference between those words. And you hear people use them almost interchangeably, but they're not really perfectly interchangeable. They just refer to different situations. Am I looking at an expression like a quadratic polynomial, or am I looking at an equation? We find solutions to an equation, we find roots to a polynomial. So let's take a look at another example, B. If we can get to a perfect square, we can take the square root and we win. We know how to do that. So how do we complete the square here?
By
You
adding
add
one
one to
again.
both sides.
If we add 1 to both sides, we get that equation. Now what?
Then you
We can
factorize to get
simplify.
x minus 1 squared.
Okay, we can rewrite this as x minus 1 squared equals 9. And now we can take our square root. And what are our solutions?
Or
4 and
-2.
-2.
4 and -2. Let's take a look at part C. This one's a little bit harder. How do we complete the square?
Add 4 to both sides.
Okay. And how did you come up with that 4?
I came to the conclusion of 4 because I realized that when I square the equation, when I multiply the non-x value, it should also multiply to another non-x value, the same value, which would give us the sum that provides 4x. And what can you add to get 4x? I said 2 plus 2. So I said it's going to be 2 times 2, which is 4. So add 4 to both sides.
Right. This is that multiply by 2 relationship that we saw previously. If we had to go backward, if we started out with x squared plus 4x, we still know that it's going to be x plus 2 because 2 is half of 4. Okay. What are the solutions?
3 and negative 7.
Good. Okay, continuing on. We're going to need a little bit of space. Let me get my copy tool. All right, let's do part D. How do we complete the square on the left-hand side?
We divide the second x value, the x to the power 1 that we there, the coefficient of that by 2, and we get a value that we then need to square and add to both sides.
Good. So we're going to add 9 to both sides. That gives us x squared minus 6x plus 9, which is equal to 56. And the left-hand side is now the expansion. If we want to package this up into a perfect square, it's x minus 3 squared. And now we're ready to take the square root. Can we simplify the square root of 56?
Yes. So 2 roots 14.
Good. And those are our two solutions. 3 plus 2 root 14 and 3 minus 2 root 14. Now E. So somebody who may be newer to this, if you've never completed the square before today, give this a try.
Should we say the answer? Or maybe you should write it down on a paper or something.
Well, tell me what to add to both sides first.
Oh, 36.
36 is correct. We take this, the 12 in the 12x term and divide it by 2. The 12x term is kind of like 6x plus 6x. And then we need to know what that square would be. 36. So we add 36 to both sides of the equation. And on the left-hand side, we have x squared plus 12x plus 36. And on the right-hand side, we have 625. The left-hand side is x plus 6 squared. There's that 6. And what is the square root of 625?
25.
25. So we have plus or minus 25. And what are our solutions?
$19 and 30 minus 31.
Good. Okay. So far, here's what we've determined. Sometimes we can just take the square root. Sometimes we have to package up a perfect square trinomial into a squared binomial. Then we can take the square root. Sometimes we have to add a constant, then package up a perfect square trinomial into a squared binomial. Then we can take the square root. So does this solve all possible quadratic equations for us?
Yeah.
No.
Yes.
I think we're almost there, but I want to test us. So let's take 3 more examples. What's different about these 3 examples?
The
They
first
have
word has a
the first
coefficient.
number of a coefficient.
Has a coefficient.
Yeah, and we call that the lead coefficient. The lead coefficient is no longer 1, but we've learned how to do. Somebody's giving an echo.
I think
Whoever has the echo.
mute all. Mr. Crawford, if you click mute all, I think it'll fix the solution.
Yeah, I just have to find my screen again. When the echo started, my screen of participants went away. Let me find that again. I like to have that.
I think they muted themselves.
They did mute themselves, but I would like to go ahead and find wherever that was, because usually I can see all of you.
Oh.
Okay, there, I got it back. Okay. So here's the thing. There is no value of a for which x plus a squared turns into 2x squared plus 4x. Why not?
Because you would only have one x squared. They're not 2x squared for you to merge them because they're like terms.
Right, x plus a squared is going to have x squared as, just a 1 lead coefficient. We're never going to make those match. What could we do with the equation in part A to make that happen?
You could
We
divide
could
the
factor
whole
2 out.
equation by 2.
Yeah, we could just divide everything by 2. And now we're back to a familiar situation. What can we add to both sides to make the left-hand side into a perfect square trinomial?
1.
We can add 1.
Oh. Yeah.
And what are our solutions?
Five and negative. 1 and negative 3.
1 and negative 3 are correct. Good. Okay, let's do part B. How can we get started?
We have to factor out the 3 so that we have the standalone x squared minus all of them.
We could factor it out. We don't need to. We can just divide it. We're not going to have any need of it in the future. Okay, this is tougher all of a sudden. We have a fraction. What do we add to both sides in order to complete the square?
Two over 3.
2 out of 9.
1 over 9.
1 over 9, right. Our process has always been to look at this middle term and take half of the coefficient, which is negative 1/3, and then to square that to get the constant. So if we add that constant to both sides, now we have x squared minus 2/3 x plus 1/9. And on the right-hand side, when we combine those fractions, check my arithmetic to make sure I'm right, but I think we get 43/9.
Isn't it 42?
We added 1/9.
He's already added the one.
Oh yeah, sorry.
And so now we repackage the left-hand side into x minus 1/3 squared. Now, once again, as usual, we can take the square root. And by the way, you'll see solutions written different ways. You could write it all under one big denominator if you want. You could also write it as 1/3 plus or minus 1/3 root 43, or I could have even said root 43 over 3. I don't care too much. I like for things to be as standardized as possible because it makes it easier to look at. It makes it easier to check. And we'll talk about that a little bit later. But we're going to do one more here, part C. And I'll go ahead and tell you, I usually do everything I can not to have to deal with fractions. But there's some times when you just have to. There's some times when it's more convenient to. So, you know, we better know how to deal with fractions. So what do we do to get started here?
Divide by 12.
Okay, we're back to having a quadratic on the left-hand side with lead coefficient 1. How do we complete the square?
We can add
We add
11.
1/4 to both sides.
No, or we can add we can add 1/11/12.
Okay, I'm gonna let several people chime in here.
Wouldn't we rather add 1/4 to both sides?
So David, do you think we're gonna add 1/4?
Yeah.
What is the square gonna be on the left-hand side once we repackage it all?
1.
X plus half.
X plus what, David?
X plus half squared.
X plus half squared. That's right. You know, here we start out with you know, a coefficient to the x term equal to 1. It's an integer, but don't let that fool you. We have to divide it by 2, right? That's what we've always done to get the constant term inside the square. Sometimes that means we wind up with a fraction. So yeah, we want, you know, we have that invisible 1x. So it's 1 that we divide by 2. And we square that and we get 1/4. And that tells us what to add to both sides. So on the left-hand side, we have x squared plus x plus 1/4. And on the right-hand side, I think we get 26/12, so 13/6. Now we're ready to repackage the left-hand side. And there I added a factor, or I multiplied in a factor of 6 to the numerator and denominator before taking the square root. So we have x plus 1/2 equals plus or minus root 78 over 6. So x equals minus 1/2 plus or minus root 78 over 6. And if we wanted to, we could write these as minus 3 plus or minus root 78 all over 6 if we want a common denominator.
Please, how did you get a 78 over 6?
Was that you, Non-Orly?
Yes.
Can you repeat that for me?
How did you get a 78 over 6?
Okay, here's what we do. If we want to take a square root, we don't like having radicals in denominators. So I'm going to cleverly multiply by 1. I'm going to multiply this by the square root of 6 over 6. Now we can bring the square roots together and say 13 times 6 over 6 times 6. And that gives us the square root of 78 over 6 squared. Now we can rewrite that as the square root of 78 over the square root of 6 squared. But we can take the square root of 6 squared. That's just 6.
Okay, I get to know.
Good, good. Okay. So we are ready for something fantastic. Up to this point, we've been solving one quadratic equation at a time. What's better than solving one quadratic equation at a time?
Solving
Two quadratic equations at a time.
Solving 2 quadratic equations at a time, that's definitely better. What's better than solving 2 quadratic equations at a time?
solving 3 quadratic
3.
equations.
Keep going.
Then
7.
4, 5, 6,
Infinite.
7, 8, 9.
What if we can
Solving
solve them
simply
all at the same time? What if we can solve every quadratic equation there ever was all at once?
That would be great.
That would be really powerful.
Create a formula for it.
Okay. And here's what I'm going to tell you. What we've gone through today, you have all the principles to do this. And we're going to do it right now. And you're going to help me. And in some sense, this is maybe slightly easier because we're only going to have 0 on the right-hand side. But if you want to, you can imagine that we just took, any one of these equations and rewrote it as 2x squared plus 4x minus 6 equals 0. You can always just take all the terms and jam them on one side of an equation so that you could set it equal to 0. And there are different advantages to that. We'll talk about factoring later today, but we have everything on one side. We have it all equal to 0. So what's the first thing that we need to do? What is the biggest hurdle that we face?
We divide.
If there's a lead coefficient, we have to divide the entire equation by it.
That's right. Our first move. And somebody other than Salorm, tell me what we get when we divide out the lead coefficient.
X squared plus b over ax plus c over a.
Equals 0 over. Just 0.
Okay, not so bad. We're on our way. That's step 1. Now, what is it that we need to do with this quadratic?
We need to find a way to keep x on one side.
Need to find a way to make them four.
We need to complete the square.
Sneh has the wording right. We need to complete the square. And I'm going to prepare us to complete the square. Completing the square involves focusing in on an x squared term and the linear term, the x term. So I'm going to take that c over a and I'm just going to move it to the other side for now, just so that it's not getting in the way of our thinking. So we want to complete the square of x squared plus b over a x. Okay, how do we do that? What is it that we add to both sides?
May I try?
Go ahead.
Isaac, I figured I was wrong. It's fine.
Snake, go ahead and give this a try.
Oh, I figured I was wrong. I'm trying to recalculate.
Okay. And if you want, you can consider past examples.
We add b squared over 4a squared.
Okay, I'm not going to repeat what Salorm said yet. I can see that Salorm is ahead of the game. Salorm knows this derivation, which is good. Somebody else tell me, how is it that we figure out what to add? Here's an example. X squared plus 20x. What do we add?
400.
Not
The square.
Not 400.
It's 100. 100.
It's 100, right.
100.
We take that 20 and we divide it by 2, and then we square that, right? Because the x plus 10 squared has x times 10 and 10 times x, so we get 20x in the middle. So we take whatever is in the middle and we divide it by 2 and we square. Whatever is in the middle divided by 2 square. So
would that be b out of 2a squared x?
that's right.
So that, and then that's b squared over 4a squared.
That's right. So now to both sides we add b squared over 4a squared plus b squared over 4a squared. And I'm going to go ahead and give you a pep talk here. Look, this looks horrific if you haven't done a lot of algebra yet. Trust that it's going to work out. Sometimes you just need to trust that whatever is complicated, you're going to get to the end of it. And that's true about a lot of things. But the more algebra you experience, the more you'll realize this is just fine. There's nothing, it may look complicated at the end, but we'll have something and we'll understand what it is. So on the left-hand side, we get x squared plus b over a x plus b squared over 4a squared. And on the right-hand side, we get minus c over a plus b squared over 4a squared. I would like to write that with just one common denominator. But we'll do that in a moment. So how do we repackage the left-hand side now as a perfect square? Somebody who hasn't given me as many answers yet. Anahita, what can we do?
I think we could go with x plus b over a all squared. No, b.
Anahita, you cut out on me on the end. I think that you changed to the right answer, but I want to hear it again.
I said x plus b over 2a all squared.
Good. And on the right-hand side, Harshita, can you turn that into one fraction?
I'm not sure.
Telvin, can you give us a common denominator? I know a couple of the students
Can I try?
don't have microphones. Archie? Okay, non-Norley, how can we rewrite the right-hand side?
You could factorize the a, so I think you get a into bracket 1 plus 4a.
I couldn't quite understand. What is our common denominator going to be when we combine these two fractions?
Could I also try?
A.
It's not going to be a non-Norley. David, what do you get?
4a squared.
4a squared. The reason that it's 4a squared non-Norley is because we need for a and 4a squared to both be divisors of what we get. So we want the least common multiple algebraically of 4a squared. And so what we're going to do, or David, tell us, what do we do with the minus c over a term?
You multiply, wait, sorry. A goes into 4a squared 4a times. So you multiply that by minus c. So you get minus 4ac.
Yeah, we find a way to cleverly multiply by 1. Multiplying by 1 doesn't change the value of an expression, but we do so cleverly so that the denominator winds up being that 4a squared that we want.
Mr. Crawford, you missed the square on the b.
Oh, thank you. And now we can write that all with one denominator. And I'm going to rearrange the numerator here just a little bit, just because it looks nicer with a positive lead coefficient. Okay, what are we ready to do now?
Square root.
Now we take the square root of both sides. Four a squared is 2a times 2a, and that's nice. Any fraction that we have is going to have a denominator of 2a. And we are almost there. Now we just subtract minus b over 2a. And I'm going to separate the numerator and denominator of the radical expression so that we can take the square root of 4a squared and get 2a. And then usually we see these results written over the same fraction. And this is it. This is the quadratic formula, and it's very useful. There are not a whole lot of things that I'd say it's worth memorizing in math, but it's worth using this enough that you get to know it by heart. So I would encourage that. Quadratics are just so common. They're everywhere. It's good to know this. By the way, I'm going to mention that there is a special name for this part right here. And we'll talk later why this has a name, b squared minus 4ac. We're going to look at it a little bit differently at times, but we'll talk about that as we go. So that's it. We have now solved infinitely many quadratic equations all at the same time, and I just want to go and name the steps from the beginning once more. Quick summary. We divide out the lead coefficient. And that means that we are only dealing with quadratics of lead coefficient 1. Okay? And then we completed the square. We do that so that we can take the square root. And that's it. Everything else is really just algebraic organization or simplification of terms or finding a common denominator. It's those 3 steps. And if you understand those 3 steps, then you can walk through them in a generalized way and you can derive this, and it's worth doing it. It's worth, I'm going to encourage every single one of you to find a peer, whether it's today or 3 months from now, maybe next time you're at school. Find a peer and see if you can walk them through everything that we've done today. It may take an hour, but walk them through everything that we've done today and have them learn to derive the quadratic formula. If you can teach it to somebody, you know it so well that you own it. And that's what you want to do. You want to own it.
Mr. Crawford,
Yes.
I just have quick 2 questions.
Sure.
Is the part you said, you've already written it down. I was going to say is the discriminant, the part in the square root, and I was going to ask about the minus b over 2a being used to identify, I think it's an x point in a graph, a quadratic graph. Is it the x point?
Oh, you're talking about like the vertex of a parabola?
Yeah.
Yeah, the vertex of a parabola has to do with the minus b over 2a. And I'll go ahead and tell you this without writing out a problem immediately. And maybe I'll get to this later today. I wasn't sure how far I could get with all of you today. So I left it open-ended, what we're going to do at the end. But maybe we'll take a look at a couple of examples of parabolas. And we will see that once we complete the square, that whatever it is that makes that square 0, that's the vertex of the parabola. So we'll talk about that again when we get there. Let's see, somebody has a question. Okay, Harshid, I understand you. You're unable to talk with us, so I won't call on you unless I can look at the chat. Okay, let's go ahead and move on. Okay. Dun, dun, dun. X squared equals -1. How do we take the square root?
Isn't it sort of impossible because you can't find the square root of a negative number,
But
because any
I read
negative number
from
will be a positive?
AOP's book that in math there's a number which is square root of -1. I'm not too sure about.
I think that's I.
Yeah, isn't it lowercase I?
Okay, so a few of you have done some reading and you've discovered I.
Yeah,
So,
I've actually learned quite a bit of I, and then there's even patterns with I squared, I cubed, and I to the power of 4 with 1 and stuff.
good. And so as part of homework tonight, so it is correct that there is a part of AOPS Volume 1. David, can you tell us what chapter that's in? Look up complex numbers.
Let me see if I can find.
I think it's in the first 2. I'm not sure, but it's in the beginning of the book.
Find that chapter and as homework, work exercises from that chapter. So here's the thing. We want there to be solutions to all these equations. And so we take this number, the square root of -1, and when we think about it, it's not a positive number because a positive times a positive is a positive. It's not 0. 0 times 0 is 0. It's not a negative. Negative times a negative is a positive. But this number it's a thing. It exists, but we call it an imaginary number. We give it the name I for imaginary. And we're going to see I a lot moving forward. So this is a new type of number. It is not on the real number line. It's somewhere else. But we're going to learn how to use it. So if I squared is -1, what is the quantity 2I squared?
-2.
It's not -2.
-4.
Is it 4?
It's -4. Okay. What is the quantity 4I squared?
-16.
Good. What is 2√3I? I'm going to put a negative out in front. What is -2√3I squared?
6.
-12.
-12 is correct. 2√3 squared is 12. Pardon? Okay, I'm going to give you all a moment to find the solutions to each of these equations, and I'm going to go refresh my drink real quick. Okay, what are the solutions to B?
2I.
Good. What about part C?
Plus or minus 2√5I.
Good. Yeah, and we can think of this as separating the square root of -1 from the square root of 20. And then we can simplify the square root of 20 as 2√5. Okay, part D.
Plus or minus √23I.
And part E.
Plus or minus 30I.
Okay, so now we can take the square root of positive numbers, negative numbers, and 0. So I just want to point this out. Even when the discriminant is less than 0, we can find solutions. Those solutions are not the usual numbers that we deal with. They're not necessarily real numbers, but we can still find solutions. All right, so we have this new type of number, this imaginary number. Let's let me think for a moment. Okay. So here's the thing. We're talking about a different type of number now, these imaginary numbers. Now, these numbers are not on our number line. And I'll go ahead and say, imaginary numbers was a poorly chosen label. These numbers do exist. They exist, and we work with them very often. We do a lot with them. But let's talk about where they are. So here is a number line. I'm going to call it the real number line. Just keeps going and going in both directions. But now we have these new numbers, imaginary numbers, and we can put them on their own number line. We have a new unit, I. And as we've seen, we can have multiples of I. And these numbers obey a lot of the same properties as the real numbers. If we add two imaginary numbers, we get an imaginary number. I plus 3i equals 4i. You can think of that as 1 times x plus 3 times x equals 4x. Okay? So there is something that these two number lines have in common. What is that?
The coefficients of I are equal to the real numbers on the number line.
That's true. The scalars, the coefficients of I are all the real numbers. What else? In a literal sense, what do they have in common?
Maybe that they both have zeros.
They both have 0. 0 is this one special number that sits on both the real number line and the imaginary number line. Well, so there's something wrong with my drawing. I don't have 0 in the same place. I have it in 2 different places. How do we fix that?
You merge the number lines somehow?
We merge the number lines. Good idea. So here's what I'm going to do. I'm going to draw that real number line right there. And then I'm going to draw a second number line perpendicular to the first. And this one we're going to call the imaginary number line. And so I just want to point out, if I were to, put the number 5 on this plane, sorry, 4, it would be right there. If I were to identify the number 3i on this plane, it would be right there. Okay, so we've talked a little bit about these two types of numbers. We know the properties of the real numbers. They are closed under addition. Do you all know the word closed or closure?
I think you...
Yes, kind of.
What does closure mean?
You said it had something to do with the fact that what I do remember was that we said division cannot be part of closure because of the fact that it doesn't divide zero.
Okay, good, Salorm. Here's what closure means. If the elements of, if any two elements of this set can be added or apply any operation to them, and we still get an element of the set, then we say that set is closed under that operation. So the real numbers are closed under addition, they're closed under subtraction, the real numbers are closed under multiplication, but because of division by zero being undefined, it's not closed under division. So tell me, are the imaginary numbers closed under addition?
Yes.
Yes.
True. Are they closed under subtraction?
Yes.
True. Are they closed under multiplication?
Yes.
Yes.
No.
Oh, we have an argument. If the answer is no, what is a counterexample?
I think I times I would give you -1, which
Yeah,
is
that's our
not.
simplest counterexample. I times I is -1, which is real, not imaginary. So the imaginary numbers are not closed under multiplication. They're also not closed under division. So anyway, I just wanted to have that conversation real quick. So, pardon. So now these numbers are closed under addition and subtraction. So I wonder, can we add a real number and an imaginary number?
Yes, you won't get an integer. For example, if you add 3i plus 4, the answer is 3i plus 4.
Okay, if we take these two numbers and add them together, we're going to get the number on that point, which is 4 plus 3i. Yeah, we might as well talk about adding these numbers. There's nothing that prevents us from doing so. Okay, so by the way, we are now working in what we call the complex plane. Now, you're used to the plane called the Cartesian plane, the XY plane, right? Well, the XY plane is called the Cartesian plane. This one is called the Argand plane, named after a different mathematician. But usually you just hear the complex plane. There's something nice about the complex plane. Notice that all 3 points that we've plotted on this plane, we've just expressed as one number. The last point that I drew, we didn't call it 4, 3. We didn't have 2 coordinates. We just had one single number. And the more you learn about these numbers, the more you will find an advantage in using them with geometry and planar algebra. And by the way, I said complex plane, but I didn't introduce that word. We're now talking about complex numbers, right? Complex numbers are all the numbers that are, well, they include the real numbers. What is complex? Complex number is any number in the form a plus bi, where a and b are real numbers. Imaginary numbers are the bi. The real part is the a. So we have a real part and an imaginary part. So somebody tell me, is the number 7, is that a complex number?
No.
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 Can we write it in the form a plus bi, where a and b are real numbers?
Yes. 7 plus 0i.
7 plus 0i. So is it a complex number?
Yes.
Yes, it is. All of the real numbers are complex numbers. Complex numbers are, it's just a wonderful set. It allows us to do all kinds of things that we could not do before, right? You're going to grow to realize that the real numbers are kind of overly simplistic. No, we love the real numbers. They do a lot for us. But the complex numbers are this much, much bigger set of numbers, and it takes longer to learn to use them. And here's what I like to point out is, if we draw out like, kind of like a Venn diagram of these sets, this big set right here, I'm going to call that the complex numbers, and I'm going to write it as a bold C. And then within that, we're going to have this tiny little group of numbers that we call the real numbers. And this tiny little group of numbers, I say group, I should use the word set. Those are the imaginary numbers. And right here, those two sets have this one point of overlap. And what is that number?
Zero.
Zero. Zero is a real number. Zero is a complex number. It's an imaginary number. It's all these things at once. Zero is just totally special. And if you want, you can imagine that we have googly eyes and a face. Anyhow, all right, so complex numbers. Every point in this plane is associated with a complex number, and every complex number is associated with a point in this plane. Now I have a question. Can we multiply two complex numbers? Are complex numbers closed under addition?
Yes.
No, I don't think so.
Yes, they are closed.
Yeah.
Let's see, if we call one of them A1 plus B1I, actually, let's just call it A plus BI. We take one complex number and add it to another. Is the result a complex number?
Yes.
Yeah, it would be A plus C in brackets plus B plus I.
We can add them and get a complex number. We can subtract them and get a complex number. Can we multiply complex numbers?
Yes, and then
Yes.
I would become a
I would become -1.
Just like when we multiply two binomials, we wind up with 4 pieces when we expand it all out. And now we can compute those pieces. What is 3i times negative 5i?
Negative 15.
Negative 15 I squared.
Oh, we have a debate. Is it positive 15 or negative 15?
It's positive 15.
Mr. Crawford, should it be 8 plus 12i instead of 6 plus 12i?
Yes, thank you. So what we get is minus 15i squared, but I squared is negative 1.
so then it becomes plus 15.
So it becomes plus 15. And so 2 of the 4 terms turn out to be real numbers. 2 of the 4 turn out to be imaginary numbers. And now we can group like terms. Now, there's only so much we can do in one day, but I'm going to show you something interesting. Let's create the idea of absolute value with complex numbers. And this wasn't part of my plan today. I just kind of thought I'd bring this in since we're talking about complex numbers. What does absolute value mean? If we take the absolute value of a real number, what are we saying?
We're
saying we're taking the value without the operation or the or other effect on it. So it's not negative and it's not positive. We're just taking the number.
Okay. I'm going to describe absolute value as size. And you may be thinking, size of what? Here's 0 on the number line. This is just the ordinary real number line. Here's 0. And if we take any number and we call it A, then we say, actually, let's say any 2 numbers, A and B. And we take the absolute value of A minus B, and that is the distance between or from A to B. And so if we have just the absolute value of a number itself, then that's the absolute value of A minus 0, which is the distance from A to 0. If A was negative, then that distance is negative A. If A is positive, that distance is just A. So size, and in the case of moving along a number line, that's distance. So there are going to be many times in mathematics you see those up and down bars around a number. Remember that that's talking about some kind of size. And usually you can determine what that means from context, or you can look for that context in order to learn what type of size you're talking about. Here's an example. If I said the set A is the set 1, 2, 3. If I ask for the size of A, I'm asking for the number of elements of A. And some of you may have seen this notation already. It's very similar. So what would the absolute value of a complex number be?
It should be a real number.
It is going to be a real number. It is going to be a distance, but distance to what?
To 0.
Distance to 0 in the complex plane. What is the distance from 4 plus 3i to 0 in the complex plane?
7.
No. 5.
We apply the Pythagorean theorem, and we get 5. Now, I want to point something out. We multiplied 2 complex numbers earlier. Let's take a look at all of the absolute values. What is the absolute value of 2 plus 3i?
2 squared plus 3 squared.
Root of 13.
Okay, how about the absolute value of 4 minus 5i?
3.
Root.
It's not
Root
3.
of
We're not
41.
subtracting a negative. Yeah. It's going to be root 41. Now let's look at the result when we multiplied 2 plus 3i and 4 minus 5i. What is the absolute value of 23 plus 2i?
23 squared plus 2 squared is 529 plus 4, 533. Root 533.
Now I'm going to point something out. That absolute value carries through multiplication and division of complex numbers. That's worth knowing. It's worth understanding. It does a lot of things for us. At the very least, you can use it to check your work. But you'll learn other uses. So now this has been kind of an aside here, right? I didn't intend to do a whole lot with complex numbers today, but this is a very nice aside. It helps us understand the whole of the subject of quadratic equations. This is the reason complex and imaginary numbers were invented, because we wanted to be able to talk about the solutions to all quadratic equations where the coefficients are real numbers. And I'm going to share something very special with you. And this is something, if you want, you can see if you can demonstrate why this is true. But if we were to write if we were to write a quadratic equation with complex numbers as its coefficients, here's something special. I don't even have to do the work. I know that the roots, or the solutions, it's an equation, or I could say the roots of this quadratic expression are themselves complex numbers. Now remember, if I wrote this equation with this expression, if I wrote a quadratic expression using just real numbers as coefficients, it's not necessarily true that the roots are real numbers. In fact, I just wrote one here where the roots are non-real numbers that happen to be complex numbers. So the real numbers are not good enough to work with on this level, right? We can have a quadratic that uses real numbers, and the roots of that quadratic are themselves not within the set that we're working in. However, complex numbers are good enough. If we write everything out in terms of complex numbers, our solutions are necessarily complex numbers. And because of that, we say that this set of complex numbers is algebraically complete. So we need them to talk about all the different things that we can do with quadratics. Okay, let's take a look back at the quadratic equation. Let's say that we are just using real numbers. A, B, and C are real numbers. Now, as I said, the solutions are not necessarily real numbers, but how can we tell? What could possibly, if A, B, and C are all real?
You check if the value of b squared minus 4ac is positive or negative.
Right.
Or equal to 0.
Yeah.
Yeah. This part is real. This part is real. So long as a is not equal to 0, then we don't, we don't eject ourselves from the set of real numbers from that. The only thing that we have to worry about is this piece right here. That's the only part that could that could remove us from the real numbers. So what we say is, if b squared minus 4ac is greater than 0, then it turns out that we have 2 real roots. If b squared minus 4ac is 0, then we have 1 real, we call it a double root. Do you know why we say that we have a double root?
Because it's the same value twice, so it's the value is squared. Let's say x plus 2 is squared. So
Yeah, and part of it also, if you have an nth degree polynomial, we say that there are necessarily n complex roots to such a polynomial. And we count the double roots twice. When we have higher degrees, we might have triple roots or of higher order. We want to count those multiple times in order, and this keeps the language that we use in polynomials, it keeps that language sort of justified or balanced, so that we can say that every quadratic has 2 roots. Right? We go, well, wait, x squared equals 0. Well, that just has 1 root. But no, we say that it has 1 root twice, is the way we count it. That way we can make a statement like every quadratic has 2 roots. So anyhow, we have 2 real roots or 1 double root, or we have, if b squared minus 4ac is less than 0, then we have 2 non-real complex roots. Why didn't I just say complex roots? Why did I need to add this word non-real?
Because real numbers are also complex. As we said, 7 can be written as 7 plus 0i.
Right. And the real point is that they are not real. It's that discriminant is negative, and we take the square root of a negative number. And so we don't just end up with roots that we know are complex, because complex includes real numbers and non-real numbers. But specifically, we have non-real complex numbers. So that's one reason to pay attention to the discriminant.
Mr. Crawford?
Yes.
I want, in terms of using this for a parabola, is it that when you use it for a parabola, you're using it to find the points at which the parabola touches the x-axis, right? If it has 2 real roots, it means it touches 2 points on the x-axis.
Okay, let's talk a little bit about parabolas. Let's say that we wanted to, first let's quickly graph y equals x squared. For anybody who has not seen one of these before. Y equals x squared, and I'll plug in x equals 0, and that gives us y equals 0. I'll plug in x equals 1, and that gives us y equals 1. X equals negative 1, y also equals 1. In general, we're going to get symmetry, right? If I plug in 3 and get 9, I can plug in negative 3 and also get 9. So we wind up with a symmetric curve. And if we connect these points and they go up faster and faster and faster, we wind up with this symmetric upward shaped smile, people sometimes call it. And so that's a parabola. And here's another example. We'll do this one in red. Let's say y equals x squared plus, oh, so no, x squared plus 2x minus 3. And now I could start plotting points again. But here's the thing, this one is not going to be symmetric about the y-axis. There is an axis of symmetry. But in order to find that axis most easily, we're going to complete the square. How do we complete the square?
In the case of this number, you would look at the -3 and look at factors of -3 and see which factors, when you add them together, or so yeah, when you add them together, will give you a product of 2. Sorry, sum of 2.
Plus 3 and minus 1.
I'm not asking what the roots are. I don't want to factor this. What I want is to engineer symmetry. And completing the square will help with that. So I just want to know, what constant do we need to add in order to complete the square?
3.
Minus 1.
-4.
Oh, whoever
I
said
think
minus 4 is close.
Minus 1/4 or 1/4, I'm not sure.
Oh, we were doing this just fine earlier. Somebody may have said it, maybe I didn't hear you.
Isn't it 1?
We want a plus 1 on the right-hand side.
It's a 4.
So we add 4.
4.
So we have y plus 4 equals x squared plus 2x plus 1. Y plus 4 equals x plus 1 squared. And now, if we want, and a lot of people do this, we move that 4 back over to the right-hand side as a minus 4. Now, I want to know the smallest possible value of the right-hand side. And maybe I should ask, what is the smallest possible value of any squared real number?
0.
That's right. And we're going to codify that fact into the trivial inequality. If x is a real number, x squared is at least 0. A negative times a negative is positive. 0 times 0 is 0. A positive times a positive is positive. This trivial inequality will wind up playing a tremendous role in mathematics. So here, we know that x plus 1 squared is at least 0, right? When does x plus 1 squared equal 0?
When x is minus 1.
When x is minus 1, okay. So I want x plus 1 squared minus 4, so I'm going to subtract 4 from both sides. So tell me, what is the smallest possible value of x plus 1 squared minus 4?
Wouldn't that make it -4?
1 and 3. So -1 and 3.
I'm not asking about the roots yet. I just wanted to find out what the smallest possible value of this quadratic expression is, so long as we stick to real numbers. And what we did was we rewrote it by completing the square, and then we used the trivial inequality we know that the square part must be at least 0. So the square part minus 4 must be at least -4. And that tells us that our original quadratic is at least -4. And where does it achieve that minimum value, Salorm?
In the x against the 2, so x would be...
Where does this happen?
I think in the line x minus 1, x equals to -1.
X equals -1 gives us x plus 1 squared equals 0. So when x is -1, and that happens at this point right here, that's the lowest point on our parabola. And then if we go outward from -1, right, plug in here. When we go up to 0, now we have 1 squared minus 4. If we go down to -2, we have -1 squared, which is 1, minus 4, which is -3. Now if we plug in, if we go 2 up from -1, plug in 1, we get 0. If we go 2 down
0
from -1, we get -3, which is also 0. We wind up with a very similar looking curve. In fact, it is exactly the same. It's just moved over a little to the left and a little bit up. So, Salorm, the answer is, if you want the vertex, just complete the square. And this is exactly why I said very early on today in today's class, I said, it's not the quadratic formula that will do the most work for you in the most different places in algebra. It's completing the square. So now somebody brought up the point that we could factor the original quadratic. And yes, we can. We haven't talked about factoring too much today, but x squared plus 2x minus 3 is equal to x plus 3 times x minus 1. And that helps us see that the roots are -3. Either x plus 3 equals 0, if we set this thing equal to 0, or x minus 1 equals 0. So our roots are -3 and 1. And those are the places where the parabola, that is the image of this quadratic, those are the places where it touches the x-axis. That's where y equals 0. When y equals 0, we're just finding the solutions to that quadratic equation. And we get those intercepts. The y-intercept is easier. We just
Mr. Mathew.
x.
Mr. Mathew.
Yes.
How do you get the 2x from the factoring here? Because 3 times x will give you 3x.
3 times x does give us 3x. And then x times -1 gives us what?
Oh, okay, I get it. Thank you.
And so, like I told you at the beginning of class, I wasn't sure where we were going to go today, but the next place we were going to go is factoring. And I'm willing to stay a little bit of extra time today. I want to make sure that we can do, that we talk about some factoring. And unfortunately, I'm going to do this quickly. If I multiply, let's say, x plus 10 times x minus 3, we get x squared plus 7x minus 30. Now, let's take a look at where all these pieces come from. Well, that 7 came from 10 plus -3, and that -30 came from 10 times -3. So in general, what we're trying to do in factoring is find two pieces that make a sum and a product as we want them. And goodness, I can't think of a good lesson I could just do in 5 minutes this way. But I am going to do something slightly different. I'm sure that you have many resources from which you can study factoring, and I would encourage you to go to those now. But we're going to do something slightly different at this moment that you're not going to have as many resources to find out about. Let's multiply out x plus r times x plus s. What do we get?
X
X
squared plus xs.
rs plus.
Have I done that correctly?
Yeah.
Yep.
Yeah.
Okay. And we could also
Yes.
write this as x squared plus r plus s, x plus rs. And that's what I'm doing over here. So if we unmultiply, then we're factoring. And we can play with the numbers until we make them right. And some of that's going to require some number sense. What about part B?
X squared minus sx minus rx plus rs.
And if we wanted, we could write this as x squared minus r plus s, x plus rs. And now we've written, the roots of the first quadratic are x equals -r and -s. But here we have a quadratic whose roots are r and s. And part C also has roots r and s. Now here's what part C is really about. It's about two ways to write a quadratic. Now, whenever it is you have two ways to express the same quantity in mathematics, you have something great. You can equate those two ways, and, well, sometimes special stuff happens. So let's see. In general, we can write a quadratic as ax squared plus bx plus c. But if the roots are r and s, we just saw that we can write that same quadratic as a times x minus r times x minus s. And I would like everybody to work on expanding the right-hand side while it is that I give my cat back to the other side of the apartment.
Mr. Man,
Yes.
which of them was it? Which of your cats was that?
Can you repeat? Part of that came out, part of that got distorted.
Which of your cats was that?
Oh, that's Nissa. Her name is Nissa. Okay, so now let me know if I've made any arithmetic mistakes here. It's always good to check the instructor's work. We are far from perfect, and it's harder to do arithmetic than talk.
I got the same thing right now.
Oh, good. I'm glad we all have the same thing. Now, here's the thing. In order for these two polynomials, these two quadratics, to be the exact same quadratic, all of the terms must match up. Well, that's easy with the first term. They're already the same. In fact, we designed it to be that way, right? That's why we chose to multiply a into x minus r times x minus s. So now we have the quadratic entirely in terms of general coefficients, and we have a quadratic with the same general lead coefficient, but in terms of its roots. Two ways to do it, and we're testing term by term, and now we look at the middle term, and we say, oh, these must be the same. Well, what does that mean? It means that b times x is equal to negative a times r plus s x. And you know what? Let's just get rid of that x. Okay. Now, c must be equal to ars. Now, these relations, these identities, must hold. These are always going to be true. But here's the thing, we can rewrite them. If we want to isolate the roots and write them in terms of the coefficients, so roots on one side, coefficients on the other, we get r plus s equals, well, we take that first equation right there and we divide it by negative a, and we get minus b over a. And we take the second equation and we divide it by a, and we get r times s equals c over a. And these right here are known as, sometimes we call them Vieta's relations or Vieta's identities. But here's a big piece. The r plus s and rs, those are known as symmetric sums. And yeah, I know that r times s is a product, but you'll understand better why we call these symmetric sums when you see them with 3 variables at a time and 4 variables at a time. There are going to be different ways to compose the elementary symmetric sums. But let's do a little bit of problem solving with these. And have all of you seen my symmetric sums video?
Yes.
Okay, good. If that video was tough, take a look back at it and try to give it another try. After all that we've done today, it may be easier. But let's take a look at some problems that relate to this, and then we'll go ahead and call it a day. So we've got these symmetric sums, thinking of them in terms of roots. Somebody tell me, what is the sum of the roots of x squared minus 4x minus 144? So what is the formula that we just came up with before?
Was it negative b out of a?
Negative b over a. Okay.
So then that's 7 over 1, which is 7.
Good. And we didn't even need to find the roots. Turns out the roots are 16 and -9, but we didn't really need to find them, which is nice. Okay, what about part B? What is the product of the roots?
Since it's 6
out of e.
144.
Yeah, 144.
-144. C over A.
Yeah. Sorry.
And
Mr. Crawford, why is it not -7?
Why is it not -7? Just in the way these happen, we have negative B over A or positive C over A. And it happens because of the number of times we use a negative multiplication sign along the way. Do we have an even number of negative signs or do we have an odd number of negative signs?
Okay, thank you.
So in part C, what is the sum of the roots of that wild-looking quadratic equation?
It would just be negative b over a, which is negative 2020 over 2019.
Yeah, and how glad are we not to have to find those roots?
Really?
That's a lot of computation.
What's the difference between C and D?
Well, it's the same quadratic, but I'm sorry, I meant the product of the roots.
Okay.
I copy pasted without changing the word. What is the product of the roots?
It's
-1
negative C over A, right?
It's C over A.
Oh.
Negative B over A is the sum, C over A is the product. So now let's do some slightly creative stuff. R and S are the roots of that quadratic. What's R plus S?
R plus S is 7 over 2.
Good. Negative B over A, which is 7 over 2. And then part B.
That's 23 over 2. Sorry, minus 23 over 2.
Well, what if we wanted R squared plus S squared?
Could we square the B and the C and the A?
Yeah. We can take this result over here. We get squares of R and S when we square R plus S. And this is why elementary symmetric sums are so cool, because any symmetric polynomial can be built from them. And so it's just a matter of putting them together as we need. Now we can subtract 2RS. So R squared plus S squared is R plus S squared minus 2RS. And now we can take our results from parts A and part B and say, well, that's 7/2 squared minus 2 times R times S.
Which is 23. So 49 over 4 plus 23.
I think I did my arithmetic correctly.
Let me check.
And finally, let's do part D.
Yeah, it's correct.
1 over r plus 1 over s. How can we do that?
Well, we know that 1 over r plus s. Yeah, so 1 over r plus 1 over s is the same thing as 1 over r plus s. So it'd be 1 over negative 7 over 2.
It's not 1 over r plus s. These things are not the same.
It's 1 over
you have to do
rs.
cross multiplication.
Yeah, it's the same as 1 over rs.
We have to find a common denominator, and we end up with the sum over the product.
Wow.
And our sum is 7 halves, and our product is negative 23 halves. So we end up with negative 7 over 23.
Yeah.
Okay. Well, let's go ahead and call it a day. I was hoping that we would get into factoring because I do know a few cool factoring techniques, but this is a whole lot of algebra for one day. And I still need to, I wasn't sure exactly where we would go with this. So what I'm going to do is I'm going to edit this document, and by morning time, you'll have this document to study before the test. And in the meantime, you can look up these topics in the AOPS Volume 1, and you can study some complex numbers there. You can continue to practice with your quadratic equations, and we'll see what we can come up with for good test problems tomorrow. Hope you enjoyed it, and I will see you all on Friday.
Thank you. See you.
Thank you, Mr. Crawford. Bye.
Okay, thank
Bye.
you. Bye.
Thank you, Mr. Crawford.